Imagine you're standing under a crystal clear night sky. You see thousands of stars glittering above, stretched across the Milky Way. It feels like you're looking at everything there is. But here's the twist. Everything you see, the stars, the planets, the glowing gas clouds, accounts for less than 5% of the universe. The rest? Well, that's where the mystery begins. A hidden world lurks in the dark, shaping galaxies, sculpting cosmic structures, and dictating the fate of the universe. Astronomers call it dark matter. It's invisible, it doesn't shine, and you can't touch it. Yet without it, the night sky you just imagined wouldn't even exist. The stars wouldn't hold together. Galaxies would fly apart. The universe itself would look nothing like it does today. Dark matter has been called the invisible glue of the cosmos, not because it literally sticks things together, but because gravity from this hidden mass holds galaxies intact. Picture our Milky Way. Hundreds of billions of stars whirl around its center, like cars speeding on a racetrack. By the rules of gravity, the stars at the edges should fling away into the void, but they don't. Something unseen is anchoring them. This was first noticed in the 1970s by an astronomer named Vera Rubin. She measured how stars orbit in galaxies and found something shocking. The stars weren't slowing down at the edges as physics predicted. Instead, they were moving too fast. The simplest explanation? Galaxies are embedded in vast, invisible halos of matter, a substance we can't see but whose gravity we can measure. That was the smoking gun. So, what exactly is dark matter? Here's the problem. We don't know. It's not made of atoms, the familiar protons, neutrons, and electrons that build everything from stars to people. If it were, we'd have seen its fingerprints in our telescopes and particle detectors by now. Dark matter doesn't absorb light, doesn't emit it, and doesn't reflect it. In fact, light passes straight through it, like glass that's infinitely transparent. What we do know is how it behaves. It has mass, it clumps together under gravity, and it outweighs all the visible matter in the universe by about 5 to 1. Imagine 5 invisible marbles for every visible one. That's the true balance of the cosmos. Vera Rubin's galaxy rotation curves were the first solid evidence, but they weren't the last. Another piece of the puzzle came from galaxy clusters, the largest gravitationally bound structures in the universe. In the 1930s, Fritz Zwicky noticed galaxies and clusters were moving way too fast, as if the clusters contained far more mass than what telescopes revealed. He called it dunkle materie, dark matter. Later, astronomers used X-ray telescopes to measure hot gas in galaxy clusters. That gas should have drifted away unless something massive was keeping it bound. Again, the answer was dark matter. Then came gravitational lensing. According to Einstein's theory of relativity, massive objects bend the path of light. When astronomers mapped how distant galaxies were distorted by foreground clusters, they could literally see dark matter's fingerprints in the way space itself was warped. Perhaps the most famous case is the Bullet Cluster, two colliding galaxy clusters. The hot gas from the collision slowed down and clumped in the middle, but the gravity, revealed through lensing, was offset, pointing to invisible mass that sailed right through the crash. The Bullet Cluster became the cosmic crime scene, proof that most of the mass was invisible, separate from ordinary matter. At this point, you might be asking, why does it matter? If we can't see it, who cares? Here's why. Dark matter isn't just an add-on. It's the backbone of the cosmos. Without it, galaxies wouldn't have formed in the first place. After the Big Bang, the universe was a nearly uniform soup of particles and radiation. Tiny fluctuations in density existed, but they weren't enough for normal matter alone to collapse into galaxies. Dark matter changed that. Its invisible gravity amplified those fluctuations, pulling matter together, creating the first stars and galaxies. Think of it as the scaffolding of the universe, an invisible skeleton upon which everything else was built. Without dark matter, there would be no galaxies, no stars, no Earth, no us. So what could dark matter actually be? Scientists have proposed several candidates, some stranger than science fiction. One idea is that dark matter consists of WIMPs, weakly interacting massive particles. They'd be heavy, invisible particles that interact only through gravity and the weak nuclear force. Another candidate is the axion, a hypothetical ultralight particle that could act like a cosmic field, subtly influencing photons. Then there are sterile neutrinos, cousins of the ghostly neutrinos we already know, but even harder to detect. For decades, giant underground detectors have been waiting for a single dark matter particle to collide with ordinary matter. So far, the results have been frustratingly quiet. Particle colliders like the Large Hadron Collider have also searched for hints, new physics that could point to dark matter. But nothing conclusive has emerged. Some researchers even ask whether we're barking up the wrong tree. Maybe dark matter isn't a particle at all. Maybe our laws of gravity need a rewrite on cosmic scales. This is the idea of MOND, modified Newtonian dynamics. But most evidence still favors the particle hypothesis, something unseen, lurking, waiting to be found. Even though we can't see dark matter directly, we can map it. Surveys like the Dark Energy Survey and the upcoming Euclid mission from the European Space Agency use gravitational lensing to chart dark matter across billions of light years. These maps reveal a cosmic web, vast filaments of dark matter stretching across the universe, with galaxies like dewdrops strung along invisible threads. Supercomputer simulations take these maps and run the physics forward, showing how dark matter's gravity shaped the large-scale structure we see today. When compared to actual galaxy surveys, the match is uncanny. It's as if we discovered the hidden architecture of reality. Yet, the biggest question remains: what is dark matter really? Every time we think we're close, it slips away. If we do discover it, the implications would be profound. We'd finally understand the true inventory of the cosmos. It could revolutionize physics, opening the door to new forces, new symmetries, even new dimensions. If we don't, then we face an even stranger possibility, that our entire framework of physics is incomplete. That gravity, the oldest force we've studied, still holds secrets we can't grasp. Either way, the chase for dark matter is not just about filling in a missing puzzle piece. It's about confronting the limits of human knowledge. It's about realizing that most of reality is still hidden from us. And it's about the wonder of living in a universe that still has mysteries left to solve. So the next time you look up at the night sky, remember, you're not seeing the full picture. The stars and galaxies above you are just the tip of the cosmic iceberg. Beneath that visible surface lies a vast, invisible ocean, one that binds the universe together. Dark matter, the invisible glue, the silent architect of the cosmos. And though we may not yet see it, we feel its grip everywhere, shaping the universe and shaping our destiny to one day uncover its truth.